Hello everyone, and welcome to this short video about antenna array placement for aerospace application using AntennaMagos and CST Studio Suite. To do so, let's start to accelerate the antenna design and modeling process for the array element in AntennaMagos. In this case, we are going to design the antenna in X-band, and the specification chooser greatly simplifies finding suitable antennas for the desired application. According to the goodness factors, we select the stacked rectangular Bradman patch and we add the prototype to the collection to analyze the performance with a new design. To do so, we have to incorporate a real substrate to the analysis. And then estimate the performance. You will find the result to your right, reflection coefficient, which fill our requirement, and radiation pattern. Once we obtain the desired parameter, we can export the complete model to CST. The exporter file is loaded in CST, and we can check that the model is fully parametric. All electromagnetic project settings are configured when the file is exported from AntennaMagos, as we can check in frequency range and the boundary condition that is parametric, which is in open area space because we are working with an antenna. You can set up the mesh properties, reducing the number of cells if you need to speed up the simulation. Open Time Domain Solver and start the simulation using -50 dB for the accuracy. At the end of the simulation, go to the navigation tree to check the result of the S11 parameter. You can observe that you have a similar result with the AntennaMagos. Sometimes we have to optimize or parameterize some variables. And the radiation pattern for a certain frequency with 8.3 dBi of realized gain. If your element is ready, you can continue with the array design. Save the project as array task. In CST, select the array task from the simulation project. This task helps you to design the array. Specify the array layout property with a 4x4 element and adjust the dimensions between elements to the ground plane. Enable mirror selection in X and Y axis. This feature is more effective for a massive array and set some elements as passive. Select the excitation pattern and specify a Taylor excitation with a relative side load level of -30 dB. Here you can check the amplitude and also the phase. Once the physical layouts as well as excitation are defined, two kinds of projects can be created, the unicell and full array. The unicell project serves to simulate an infinite array including mutual coupling. Specify the scan angles that you want to analyze and set the far field monitor, especially at 10 GHz. A new simulation project has been created. Therefore, we have to set up the simulation. Let's change the minimum Z boundary condition to electric to avoid discretizing the volume underneath the ground plane. Open the flocked port properties and toggle on polarization independent of scan angle phi. Now it's time to recreate a full array. For full array, let us select a simultaneous excitation with the operating frequency at 10 GHz. The full array is created. Now let us update the array task. The Unicell launched a parameter sweep of the 3D simulation project using a previously defined scan angle. The results shows an active element pattern, which represents the pattern taken for a single excited element in the array, with all other array elements terminated by matched loads. This active element pattern can be used for prediction of scan performance of large phase array antennas. On the other hand, for full array, we have the results for the radiation pattern with a 17.58 dBi of realized gain. These results were obtained for a 0 degree of scan angle theta and phi. Another feature in CST is antenna placement. CST offers electromagnetic solver for all electrical size. With increasing electrical size, high resolution are the recommended approach to efficiently handle large electrical size. That's why, in this case, we're gonna use assembled mode. We are going to analyze the performance of the full array on a drone. First, we need to drag and drop the drone onto the assembly mode. Because we don't have an anchor point, we have to add one to place the antenna. Then drag and drop the full array and then snap the anchor point to assemble the two models. So we have to create a hybrid solver task and select a bidirectional simulation. We have to define who is the platform and who is the source. Let us use only 3 sample frequencies, 9, 10, and 11. Let us set up the hybrid simulation. For Clover Iterative Solver, let us speed up the simulation by decreasing the maximal number of iterations and the target residual. As you can see, we are analyzing the problem for 0 degrees, theta and phi scan angles. Let us save the project and let us update the hybrid simulation. Checking the result, we can see the far field modified by the drone. Here we have the same result, both represented in 2D. So to see the variation between this simulation with the drone and full array, we have to plot both radiation patterns in the same graphic. Notice the difference between both radiation patterns, so we have to consider this result in our design. I hope this video helped you. Thanks for watching.